This video is going to focus on how these individual atoms come together to create compounds. But before I move on to any of that, I have to give a very brief introduction on these valence electrons. And so most atoms, there are some exceptions, but most atoms would prefer to have 8 electrons in their outermost layer. And again, I'll discuss what these layers are in later chapters. Basically, any electron that's in the outermost layer of the atom, and I think about it as everlasting gobstoppers or jawbreakers. Any atom that's in the outermost layer is called a valence electron. Most atoms prefer to have 8 of these valence electrons, or what they refer to as an octet. And so in a very watered down definition, the number of valence electrons is equal to the group number. And so the group number on the periodic table is the number of columns. And so sodium, for example, will have 1 valence electron, whereas fluorine on the other side of the periodic table will have 7 valence electrons. Please note that noble gases, those guys in the very last column, they are going to have 8 valence electrons, and so they already have their octet. They're nice and happy. Normally they don't bond with anything because they don't want to give up electrons or have any more added to their atom. And so now we can kind of move on to how these things kind of come about. And so example I kind of touched on in a previous video was talking about sodium and chlorine. And so sodium by itself, elemental sodium, it exists as a very shiny metal, and it's highly reactive in moisture. So much so that if you had it just sitting on your dining room table, especially in Texas when humidity never drops below 90, that stuff would ignite all by itself. And again, don't try to eat it because you might have some more issues. Chlorine is a yellow gas, and it's very, very pungent and as well as poisonous. So if you've ever gone to the swimming pool and it's closed because they're cleaning the swimming pool and it smells horrible, it's because a bunch of chlorine gas is just kind of floating around that area. So it doesn't really seem that if you mix a poisonous substance with another poisonous substance like a very good idea, right? But when you mix these things, you actually end up creating a sodium ion and a chlorine ion. And what happens here, which happens with magnets as well, if you have a positively charged sodium and a negatively charged chlorine, you end up having an attraction between these two ions. And whenever that occurs, we end up with neutrally charged sodium chloride, which we all use as table salt. And so whenever all this happens, this actually occurs through an ionic bond. And so ionic bonds occur between metals and nonmetals. Please note, one more time, metals and nonmetals. And so the metals are on the left-hand side of the periodic table. Nonmetals are on the right-hand side of the periodic table. And so whenever this occurs, there is a complete transfer of electrons. That is why on this previous slide, you have a sodium plus and a chlorine minus. Normally, sodium and chlorine in the nature, they are neutrally charged. But as soon as you interact these two, there's a transfer of electrons from the sodium to the chlorine. And so the metal atoms become what they refer to as cations. The nonmetals will always become the anion. So an easy way to remember this is cation, and the very center of it is a T. And so T looks very similar to a plus, plus. And so in this case, your cations are always going to be positively charged, anions are always going to be negatively charged. And because you have these pluses and these minuses on these atoms, they are attracted to one another. Not only are they attracted to just one another, they bring all of their friends along with them as well. And so all ionic compounds will actually come together and form what they refer to as the lattice or a 3D array structure here, where you have alternating chlorine minus sodium plus, chlorine minus sodium plus, chlorine minus sodium plus, so on and so forth. This is why if you look at a piece of salt under a microscope, it has a nice, again, crystalline structure to it. And so in these cases, you will never find just one sodium or NaCl all by itself. It always occurs in these huge structures. So the way that this happens is, as I mentioned earlier, sodium and chlorine by themselves are neutrally charged. Sodium atom, it's number 11, and so it has 11 protons and 11 electrons. Whereas chlorine, it's number 17. Has 17 protons and 17 electrons. Both of these occur naturally as neutral atoms. But the issue becomes Sodium is or has one valence electron. Because it has one valence electron, it's much rather just get rid of that one electron and become an octet. Whereas chlorine has 7 out of its electrons. And so if it sees that sodium is going to give up its electron, it's going to be more than happy to take that electron over itself. And once this happens, now sodium still has 11 protons, but now it only has 10 electrons, and so it is going to be a positive charge. Chlorine now has 17 protons and 18 electrons, so it has one more electron than proton, so it's negatively charged. This is the formation of your ions. But as I covered in the last slide, if you have a positive charged ion and a negatively charged ion, and they're relatively close to one another, they smash into each other. And this is how you get your sodium chloride table salt. You have a bunch of these sodium plus ions, a bunch of the chlorine minus ions, and all of them just kind of congregate in order to give you this table salt. So this next slide here, I ask you repeatedly as many times as I can, please, 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 please memorize it, because this is going to save your behind multiple times throughout the semester. And it's not even that difficult if you kind of just follow along with me here. Everything in group 1, and again, H, Li, sodium, potassium, rubidium, cesium, all of them have a +1 charge. Group 1 +1. Same deal with group 2. Group 2 has a 2 plus 2 plus 2 plus 2 plus 2 plus. Everything in group 2 is always going to be a +2. Please notice everything is missing from group 8 because they already have their octet. They're happy. Those are the noble gases. And again, you can kind of ignore H minus for now. But your F, your Cl, your Br, and your I, all in group 7, those are going to be in -1. And these two things are going to be -2. One thing is going to be -3. And so here, just kind of follow it up with this path. Only thing whenever you get to group 3 is ignore boron. It's letter B. It has its own issues. We'll talk about boron in the future. But aluminum, gallium, and indium, all 3 of those are going to have a 3+ charge. So, to try to help you out there, 3 things in group 3 have a 3+ charge. Ignore boron. And these other ones in the center, I can't really help you out. Just know they exist. There's only 4 at that point now. And so, ions, they always have to have a metal and a non-metal, or 2 oppositely charged ions for them to be created. On the other end of these bonding scale, we have covalent bonds. So covalent bonds, we typically call these molecules. And so a covalent bond occurs whenever you have 2 or more nonmetals. And so just to reiterate, if you have a metal in your compound, it cannot be a covalent bond. If you have a metal in your compound, it has to be ionic, because that's the only way that you can actually have a metal inside of your compound without it just being a metal by itself. So covalent bonds are going to form between 2 or more nonmetals. So unlike your ionic bonds, whenever these things form, there is no transfer of electrons. Covalent bonds occur whenever you actually have a sharing of electrons. Rather than sodium giving up 1 electron to chlorine, you have a carbon and a hydrogen sharing their electrons in the center. You're still fulfilling the octet rule, and again, this will come up a lot later chapters. But here, if you just kind of imagine these atoms like holding hands instead of just giving one whole hand over to the other person. And so one thing I do have to kind of point out about this that's a whole lot different than ionic is covalent bonds are only between the molecule themselves. And so water is H2O. It's never going to be H4O2 or anything like that. It's always going to be H2O. But whenever you have a sample of water, it's just a whole bunch of H2Os. So that's all I mean when I say the atoms are only covalently bonded to one another, like the H and the O, but it's not going to be covalently bonded to any other molecule of water. And this last slide, or second to last slide, it's not really in your book. I just have to point it out because sometimes students get a little bit confused when we start moving on here. But a molecule is going to be constructed from 2 or more nonmetals that are sharing electrons. So in these cases, you're not looking at anything that is charged. If you have something that is charged, you are now looking at an ion. And so this becomes a little bit more confusing whenever I introduce these polyatomic ions. But anytime you see a charge, it is no longer a molecule. There is no such thing as a molecule existing in an ionic compound. And so if you have a metal anywhere in there, has to be an ionic compound. No ifs, ands, or buts. If you see a charge anywhere on that chemical formula, it has to be an ion. It cannot be a molecule. And so, the last thing I need to cover here is, as I mentioned in one of my first videos, some of these elements exist as molecules. And what I mean by that is H2, N2, O2, F2, those are still elements. They are still consistent or consist of only hydrogen atoms and only nitrogen atoms and only oxygen atoms. But they are going to be bound to one another in the fact that you are never going to find an O all by itself or an H all by itself. You're going to have the molecule exist because you are still connecting two or more nonmetals to one another. In this case, hydrogen and the hydrogen atom, they're both nonmetals. So when they are bound to one another, it's still a molecule. We just call them elemental molecules or molecular elements. And so you need to be aware of all these. And then again, these guys who just sit in the center, you just need to know S8, and selenium is always going to be 8. And then phosphorus is never going to be just P, it's going to be P4. And the main reason why this may come up is if I give you a word problem and I say something like phosphorus was mixed with oxygen to give you phosphorus oxide, and you need to write out a chemical formula, you need to know not just to write P and O, because that will mess up everything before you even start on your problem.